7:30. And today we're going to finish up a little bit about the adder hardware and then talk about simplification. So we talked about it a little bit last time, but this is the delay for this is the circuit for a 1-bit full adder, right? And it has a delay of two, just call it time units. Like 2 gates. Assume that they're the same delay. And we talked about how we could connect all of these together to make a multi-bit happen by doing the ripple carries, but then you're doing for every bit 2 more gates of delay. So with this setup as our ripple carry, our delay is going to scale by the number of bits. And if we have too many bits, our delay is going to be too long, right? So this is not good for a high-speed application. So if we did this in, say, like the CPU, then our cycle time would be impacted. So we need to be able to make the same computation adders, but in a more speed efficient way. So we want specifically fewer gates in sequence. So we can create a faster adder by using our 2-level logic equations. You have the truth table for the carries. You have all of the bits in terms of input that you need in order to calculate those carries. So you can implement them with 2-level logic, right? And then if you take the equations, substitute them into each other, you get these longer equations, but they're still 2-level logic, right? So 2 gates. They just get a little bit wider as you go to the higher bits because they go from 2 input gates to 3 input gates, 4 input gates. And if you do it this way, it's again not feasible for very wide adders because the number of inputs of the gates would rise for every single one that you have. And because of the technology process in transistors, we can't have just 32 inputs into a gate. We need to limit how many inputs go into a gate. So there's this in-between approach that is going to limit the complexity of these equations in order to simplify our hardware and give us less gates with that large amount of inputs. And we're going to call this implementation a carry look-ahead adder. And there are 2 things that you're going to calculate at every bit, and that's, is this bit going to generate a carry? So it's going to generate a carry if A and B are 1. No matter what the carry in is, the carry will be generated. And then, are you going to propagate a carry? So you will propagate a carry if A or B is 1. Because now, if A or B is 1, then whatever is incoming, carry will be whatever is incoming. And then if we put it all together, we can make a 4-bit carry look-ahead adder. So for our first carry, we either generate a carry by the first 2 bits being 1, right? Or we propagate because the first 2 bits are either one of them are 1, the carry in. And then for our second bits, again, we can generate at this bit, or we can propagate from the generation of the previous one, or we can be propagating the propagation of the carry in. And then this pattern just continues. I can generate at the third bit, or I can propagate the generation second bits, or I can propagate the propagation from the generation of the first bits, and then I can propagate all the way from the first bit. So when we do this equation, we only have this one gate that is getting larger and larger at the end, rather than all of the gates. So it's a little bit of a trade-off, like it mentions in the previous slide. But the main point is that this logic is done in 2 levels, and the gates having 2 to 5 inputs at maximum for 4 bits carry look ahead adder. And then you can maybe use the 4-bit carry look ahead adder and then connect those into a real carry if you want a larger bit adder. There are other adders as well. There's carry select adders. There's carry save adders. So there's lots of different adder designs out there. I just showed you the ripple carry adder because it's the simplest, right? But it is the worst performing in terms of time. And then this one is kind of in between. It's a little bit more area because you have to calculate all of these carries without using the hardware from the previous ones, right? Because you're not going to wait for them. But it gives in between performance because now we're still 2-level logic. So this is a checkpoint for the carry look ahead. So what if we expanded it to the 5-bit adder? Is the question. And your code for today is 832. So work on this on your own first. Me too. Let's see if the answers change as much. Is anyone still thinking about this? All right, so we are well past the threshold on this one. And so we can go through this together, right? So the first thing that we were doing was at the 5th bit, right? Because we started 0. Are we just generating, right? And then what's the other way that we can have a carry? We're propagating the previous generation, or we're propagating the propagation of the previous generation between this one, or you propagate the propagation of the propagation of the other one. That's what's generating. And we go all the way back to the carry in, right? So we just follow the same pattern. And now you can see that we have 1, 2, 3, 4, 5, 6 inputs and gates here. So this one is A, the other ones have some minor errors in them. But do we see the points of the carry look ahead adder? We're no longer rippling through. Okay. So here is our individual little bits now. We have this propagation. And then we have the generation. And the reason that it's this XOR is because it mentions in the previous slide that rather than the OR, you can do this actually. And then because of this XOR already existing for the full adder, we're kind of using as double duty, right? We can reuse this hardware for a different purpose. All right, so these are what the circuit diagrams look like. Right? So you have your individual 1-bit adders, 1-bit full adders, and they create these propagations and generation bits, right? And then you have these other circuits that are taking those propagation and generation bits and calculating the carries. And then you would connect these carries to the appropriate adder. So now our deepest levels of logic are 4 inputs, 4 gates. Okay, because I go through 1, 2, and well, let's do the C3 because this one is just carry out. So I go 1, 2, and then inside this adder I go through 2 more. And then it's the same for C2, 1, 2, and then 2 more. So I'm no longer going through 8. I am at maximum 4 levels with the carry header. So we can't build a 16-bit adder this way for the same limitations of the other equation calculating the carries, right? Because if we have 16 bits, then we'd have a 16 bits inputs and gates, and you just can't make that in real life. So we could use a kind of combination between the two, where we build this 4-bit adder, and then we have the propagation and generation for the last bit of this 4-bit adder. And we make another 4-bit adder, again, propagation generation. And this will calculate the carry look ahead for the 5th bit. And then what is this going to be? The 7th bit, right? And then the 13th bit, as well as the carry time. So these are carry look aheads, and they're connected to another larger carry look ahead. And you could also just connect these all in ripple carry, right? If space was a concern for you and performance was not, the ripple carry might be the better option. So the next thing that we were going to talk about for today is multiplication. So multiplication is a little bit more complicated, but it is again going to look a lot like what we already know on how to multiply with decimal numbers, but now we have binary numbers. And it's going to take more time and more space in terms of performance and area for the circuit. Okay. So there are 3 versions of the multiplication that we are going to go over. But like I mentioned, it's going to be very similar to what we did in grade school with decimal, right? So you have your multiplicand, that's n bits, and you have your multiplier, that's m bits. And the way you would do this is you would take the first one, multiply it across all of these, and then you would have the result down here. Then you would take the second bits, multiply it across, and shift it to the left by 1, right? And then same thing, And then same thing, shift it to the left by 1, and then you would add it all together. And if you did it for these two numbers, so what is this, 8 and 9? So I would get, what is this result?
Doesn't it do?
Because this is plus
8.
plus 8. So we'll see this written out a little bit better on this slide, right? We have 1 times essentially, let's just call this what it is, 8, right? So 8 is the result. 0 times 8 is 0. 0 times 8 is 0. And then 1 times 8 is 8. And then we add them all down. Right, so multiplying by hand binary numbers, we can do this, right? The carries get a little bit more complicated. You have more ones in the multiplier and multiplicand, but you can still just do what you did before, carry them over. All right, so the basic function that we need to be able to do is multiply the multiplicand with the current digits that we're working on from the multiplier, and then add up those partial products. That's all we're doing here, right? So this is further simplified in binary because our multiplicand is either going to be just going added and shifted, or it's just going to be adding a 0. So you do nothing, right? But here is some hardware that would implement your multiplication. So what we do is we look at the current bit position of the multiplier, right? So this is our multiplier. This is where we put our 32 bits multiplier. And we have this other register for the multiplicand. And here, if the multiplier is 1, we would add 1. Otherwise, you would add 0. And then after we look at each one of these bits, you shift the multiplicand to the left by 1 bit. So we get the first bit out of here. That tells the control, am I going to be adding the multiplicand or 0 to the product? Right. So if we go back to here, our first bit was 1. In here, we would have 8. So that would tell this ALU, add 8 to product, which is currently 0, right? Then we would get the next bit is 0. The multiplicand would get shifted left by 1. It results into this, right? So it's shifted left by 1. And because it's 0, we just add 0, right? Shift the multiplicand left by 1 again. We get another 0. So we add 0. And then we shift multiplicand to the left again by 1. We have a 1 as our next current bits. That says add the multiplicand that was shifted to the product. So that's how we can get this 72 as our answer. So you're just doing addition for however many bits you have here and shifting this left. And you can implement multiplication with this simplified circuit. Are we good with this one? Because we are going to go over another circuit that is more efficient than this circuit. Okay. So product is always starting at 0, and then the multiplicand is in the right half of the multiplicand register, and then it eventually makes its way to the left half because we're shifting it to the left by 1 each iteration, right? And then the multiplier gets put in here, and eventually this register comes to all zeros. So we keep shifting the bit that we're using out. All right. So this is just a flow chart of that simplified multiplication circuits. So again, we check the multiplier to determine whether we're going to add the multiplicand or the product, or 0 to the product register. And after each iteration, we shift multiplicand to the left by 1 bit, and we shift the multiplier to the right by 1 bit to go to the next bit. So, as I mentioned, this is a simplified circuit. It is a lot bigger than it needs to be, and it's quite slow. But here is an example and a table showing the different iterations. So before you start, you load the multiplier into the multiplier register. You load the multiplicand into the bottom right of the multiplicand register, and product is 0. So first iteration, look at the multiplier, right? The rightmost bit, it's 1. So that means we add multiplicand to product. Shift the multiplicand to the left by 1. Shift the multiplier to the right by 1. Second iteration, we again have a 1 in the multiplier register's least significant bits. So we add multiplicand to product. And then shift left again, shift right again. And now for iterations 3 and 4, they're both 0 for the multiplier. So we're not adding to the product register anymore. Right? But we still shift multiplicand to the left because the hardware will always do that. And we also shift the multiplier to the left. So these iterations still happen. And it still takes the same amount of time because we don't know that it's a 0 in the hardware until we shift it and actually check, right? So this was 2 times 3 is 6. And we can double check the product register, 6. Okay. So this is the simplified circuits. Going through each iteration. Here we want to see the optimized circuits. It's not fully optimized, it's an optimized version though. So we're going to perform the add and shift in parallel. And we're going to reduce the multiplicand register from 64 bits to 32 bits. We don't need this oversized register because the real addition that's being performed every iteration is only 32 bits. So the least significant bits of the product are not going to change, but we are still going to be doing the same process. Okay. So here is our hardware. So we have multiplicand, and it's 32 bits registered rather than 64 bits, right? Product register is 64 bits still. And multiplier is still 32 bits. So the way that we are doing this add and shift in parallel is we add to the upper bits of the product register now, rather than to the product register as a whole. And then we shift the product register to the right by 1, which is the same as shifting the multiplicand to the left by 1. So we're always adding to the upper bits of the product register, and we keep shifting the lower bits to the right because we're no longer working with those lower bits. Like for this first one, after we add it to the product register, we're never touching this bit again, right? There's nothing that's going to be added to it. So that's why it's shifting to the right. And then once we finish this bit, we're never touching this bit again. Once we're finished with this bit, we're never touching this one again. So that's why we can shift it to the right and only add the upper bits. So we see that this is smaller, right? I see that it still works. Okay. So again, this is the overview of it. So initially, product register is going to contain all zeros. The lower 32 bits of the product register that are the all zeros will be shifted out. And we'll keep getting our product shifting in from the right. And we use the other thing was from this one to this one, we got rid of the multicam register, right? I mean the multiplier register. Multiplier is here, is missing here. That's because we can just put it in the bottom half product register. Because we're shifting it to the right anyways. Right? So it was going to get shifted out. We don't need this other 32-bit register. We can reuse this one. And then this is the flowchart, right? So is the first bit of product one, add multicam to the top half of the product register, and always shift the product register to the right by one. So that's shifting our product to the right so that we can add the next multicam if we need to, as well as shifting out the bits of the multiplier to get the next bits for the next iteration. All right, so here is our table for this one. So again, we're doing 2 times 3, but now we have less things to keep track of. So our initial values, multicam is 2, and then our product register, which is going to hold our multiplier in the bottom half. So we look at our product register's first bits. It's 1, so we add multicam to the top half of the product. And we shift the product register to the right by 1. And again, for the second iteration, look at the least significant bit product register. It's 1. We add the multicam to product upper bits. And then again, for the next 2, they're both 0, so we just end up shifting product register to the right twice. So here's another shift, and here's another shift. And then we get 6 once again. So this is what I'll be asking you to provide for things like homework or the exam. I will be explicit on the homework and the exam and say I want the optimized table. So the optimized circuit. Right. So then how can we extend this to sign multiplication? Well, what we can do is store the signs of the operands, right? And then convert the sign numbers to positive numbers. And once we have them as positive numbers, we can reuse that circuit and perform the multiplication between those 2 positive numbers. And then just at the end, we need to check the sign bits. If they're the same, then the sign bit is 0. If they're different, we negate the product, right? Two's common. So you would invert all the bits, add 1. So just like we could reuse the adder hardware to do subtraction by just adding a little bits of extra circuits to our hardware, we can do the same thing to do sign multiplication. So sign multiplication, we're just adding a little bit of pre-processing to convert everything to positive and making sure that we remember what the signs were. And then a little bit of processing at the end. Check, does it need to be negated? If it does need to be negated, negate it. But in the middle, the multiplication, the actual big step for the algorithm, it's using the same algorithm, right? So it can reuse. All right, so how do we do multiply in MIPS? So MIPS provides a pair of 32-bit registers, high and low, to contain the 64-bit product. Because if you are trying to multiply 32 bits by 32 bits, you need 64 bits in order to represent the possible answers for the multiply. So it has two multiply instructions. You have mult and multu. Multu is for unsigned, right? And we use this low and high to move values from the high and low registers to the general registers. And both of these instructions ignore overflow. So it is again up to the software to check to make sure that you don't have overflow. And if you do have overflow, you set those flags to try and recover or tell the user this answer is wrong. Okay. So here's the example. So you would do mult T0, T1. And this would, the result goes into this high and low register. That's why there's no RD. And then if you know that you only need the bottom bits because you're not multiplying numbers that are too large, you can do just load the lower bits into T2. And like we mentioned before, there are pseudo instructions that just gets converted into multiple instructions. It would be mult, so mul, and your results in T2, you're multiplying T0, T1, right? So again, this would be, you have to be careful with this because this would be a 32 bits. You're throwing away the upper 32 bits. All right. So the other thing that we can do is, this is the third multiplier circuit. Right? We said we would go through 3. We did the very simple one. That is easy to understand. We optimized it a little bit, reuse registers, shifting once rather than shifting in 2 different places. And this is even faster. So we're going to use multiple 32-bit adders for each bit of the multiplier. So here we have our multiplier multiplied by the multiplicand or by each bit. And that's going to give us that 32 bits result. And we have now this tree of adders in order to get our 64-bit product. Okay. So this is just adding the lower bits, and then these are adding the upper bits. So it's just doing all of the multiplications at the very beginning, and then using the tree of adders form this addition. Okay. So rather than taking multiple different cycles, right, this is going to take multiple cycles. This circuit would maybe have a longer cycle time, but it would do it in 1 cycle. Okay. So if you have a fixed amount of bits for your multiplier and multiplicand, this might be a good option if, again, area is not a concern and performance is your highest concern. And we'll talk a little bit about division for this as well. But for division, you can't do everything all at once. So you're not going to be able to do this 1 cycle hardware for division. All right, so don't leave just yet. you do have reading for next time. It's going to be division. And we'll get into starting a little bit about floating points. But what I want to do now is I'm going to post a link to Piazza. And if you can fill it out, it's going to be the mid-semester survey. So we've done homework, we've done the exam, we've done readings. I just want you to provide me with two things. 3 things that you want to keep the same and that you like. 3 things that you would like to see differently, and maybe a suggestion of what about it that you want to see different. So I'm going to post that. Let's